Hello everyone. In this lecture, we will study some algorithms for a network. So, in particular, the greedy algorithm, and its modification. So, sequence arcs. We first record the following example. So this is a graph, and we apply the Digraph, the algorithm, to find the distance tree. And of course, there might be several distance trees. And one of them is as follows. We start with A. A is our rooted point, and then we first get AB, and then from AB we get BD, and then DE. Okay, on the other hand, we have not DE. We get AC because you want the total weight is still minimal. And then after that, you have DE because this is E. This is 1. Okay, here the weight is given as in your textbook. And then you have CF. Okay. In general, if all the weights satisfy the property that any partial sum is different from another partial sum, then you can prove that following the algorithm, the spanning tree is unique. Okay, in reality, we have the following kind of minimal connector problem. So usually when people introduce some new algorithm or new notions, usually they face a kind of new problem cannot be treated by the old method. That's how reality and the theory interplay together. So there are n cities, A1, A2, AN, and it is desired to connect some of them by highways so that each city is accessible from any other. And then the cost. So we can do the following mathematical formulation. So let Km be the complete graph with vertices A1, A2, AN, and Kn omega is a network where omega aij is the cost to construct a highway between AI and AJ. Oh, so here actually the minimum means determine the way to connect such that the total cost in it is minimal. Okay. And the question is, seek a spanning tree the sum of whose edge weights is as small as possible. So here actually, when we do mathematical formulation, we already simplify the problem a little bit. In the real problem, it didn't mention the spanning tree, but if we want to minimize the cost, we can always reduce the subgraph to a tree by deleting some not necessary edges. Okay, since actually for this weight, so it's always non-negative or positive, then when you drop some tree, when you drop some edges, the cost is it's reduced. Okay. So next we introduce algorithm due to Kruskal, which is also called the greedy algorithm. So let G omega be a network, and for any subgraph HOG, define the weight of subgraph, just a summation of the weight of each edge. Okay, then a spanning tree OG that has the smallest weight of all spanning trees. OG is a minimal weight spanning tree. Remark is that even for the minimum weight spanning tree, it's not unique in general. And secondly is actually if the weight is a constant function, then any spanning tree is minimal, because then the cost from the weight is proportional to the number of edges, but for a spanning tree, the number of edges is the vertex minus the cardinality of the vertex set minus 1. Okay, and cross-course algorithm, a more common name, greedy algorithm, has the following idea. So each step we choose an edge of smallest weight and satisfy an extra condition that the fact that when terminate the chosen edges are to be the edges of a spanning tree. So in other words, there's no cycle. Okay, then the pseudo codes are as follows. Actually, greedy algorithm has many versions, and this is just one version for generating a minimum weight spanning tree. And so we still use this notion in the following. And then step 1, put F to be an empty set. And secondly, while there exists an edge alpha not in F such that F union alpha has no cycles in it that contain the edges of cycles of G and determine. So you might have several edges satisfy the no cycle condition and determine one with the smallest weight, edge alpha of minimum weight, and put alpha in F. So you increase the edge size by 1. And you repeat until there's no such alpha, then you output the final result. So from last lecture, we know a typical theorem we should prove is T is a minimal weight spanning tree. It's easy to see the spanning tree part because it's a special case of the general algorithm for generating a tree. And so the crucial statement we are going to prove is it's really a minimum weight. It really has a minimum weight. So we begin with M vertices and no edges. And hence, at the very beginning, we have a spanning graph, VF, with n connected components. Of course, here we assume G is connected. Then by the choice of alpha each time alpha joins vertices in different components of VF, and the number of connected components is decreased by 1. After you put in alpha each time. And therefore we can always find such alpha. This is not trivial, for the reason is G is connected. Okay, until we don't have any connected component more than 1. So until we have n-1 edges in F. So in that case, T has a unique connected component. Okay, then T equals VF is a spanning tree. Okay, so this is the easy part. We show that no matter how, after the algorithm, you always get a spanning tree. Then next, we will show that T is a minimal weight spanning tree. So idea is similar as before. We push the assumption to the extremo, find a certain minimal weight spanning tree has most common edges with T. And then we derive the contradiction by constructing a new one with more common edges. So let alpha 1, alpha 2, alpha n-1 be the n-1 edges of F. So F is an edge set of T in the order that they are put in F. Let T star be V F star be a minimum weight spanning tree. So for minimum weight spanning tree, you might have a lot possibilities, a lot of choices. Now you find the extremo one. Extremo in the following sense, which has the largest number of edges in common with T. So in other words, no minimum weight spanning tree has more common edges with F than F star does. Okay, then suppose that F star is different from F. Otherwise, we are done. So let alpha k be the first. Recall that alpha k is an edge of F. Let alpha k be the first edge. First in the sense of the index k, edge of alpha of F that is not in F star. In other words, alpha 1 to alpha k minus 1 are contained in F star. And then we are going to construct another minimal spanning tree. T star star OG, which has more common edges with T than T star does. Then we have a contradiction. So the technical tool we are going to use is always a lemma we proved several lectures ago, that for each edge you can add one counter edge, such that by deleting one, adding the other, you have also a spanning tree. So you have two versions of that. We use that a lot in all the previous proofs for the tree growing algorithms. Noted that, so there is an edge beta of T star such that the graph T star star obtained from T star by inserting alpha k and deleting beta is a spanning tree of G. Then by the construction, we can compute omega T star star from the information of T star. Here we use the fact that the weight is linear. So you can add one and delete one. If it's nonlinear, it's much more complicated. You might have high order terms, and then the control is not that easy. Okay, for certain problem, this is a case. For example, when you construct one edge, and then raise up the price for the fields nearby. Okay, then when you construct the other edge, the other highway, the price is not same as before. It's affected by the previous constructions. This is the case, also the case in reality. Okay. And we have omega alpha k is greater than omega beta. So our question is why it is true. Think about this, why this is true. So the short answer is T star is a minimal. T star star, you don't know it's minimal or not. So you have this. But on the other hand, since beta is a possible choice in determining the case edge to be put in F in carrying out the greedy algorithm. So please verify this. It's not that hard, but it's also a non-trivial property. And we need to care about this. And then, because beta is a choice, if omega, the weight of alpha k is strictly greater than the weight of beta, then instead of alpha beta, we need to choose beta at a k step. Therefore, beta should be less than or equal to omega beta. And then combine the reverse inequality, we can conclude omega beta has the same weight as omega alpha k. And then we see omega t star star is minimal. Since t star star has more common edges with t, we have the contradiction because we assume t star is a minimum weight spanning tree with most largest number of common edges with t. But now you have another one has strictly larger number of common edges with t. So in other words, if we turn back, check all the proofs, then you find that the problem comes in when we assume t star is different from t. Therefore, t itself is a minimum spanning tree. Okay, now let's run the program once for the following graph. We have A, B, C, D, E, F, G, and we have certain weights. And starting with A. And then it's clear, first we should choose AB. Okay, then we choose CD. Here we don't need to put in edges connected to the previous ones. Okay, we just choose the ones with smallest weight, which contains no cycles, CD. And then we have EF, then DG, EG, AG. For DG, EG, AG, we can arrange it in different orders, and therefore you might have several ways to grow a minimum weight spanning tree. And anyhow, the total weight is 1 plus 1 plus 2 plus 3 plus 4 plus 4 equals 15. And then from this example, we can see practically we can arrange the edges in a sequence from smallest to largest weight, and then iteratively select the first edge that does not create a cycle. Okay, actually the algorithm therefore consists of two parts. First is select the smallest weight, and then you have, this is the first part. Then second part is no cycle. And then the difficulty lies in the second part, testing if there is a cycle is hard. Hard means it's time consuming and you need a lot of space to restore the information. Okay, so usually when we're not satisfied with certain results, certain method, some people will come up with a desire to invent a new method to overcome the difficulty. So here's Prime's algorithm. Modified greedy algorithm, which gets rid of testing cycles. So for the Prime's algorithm, you will see we come back to the previous method that we generate a new edge based on the previous steps. So no matter how, the object, the intermediate object is always connected. It's always a subtree. Therefore, you have no need. It's not necessary to test the cycle anymore. So for minimal weight spanning tree. So the assumption is still a connected network omega greater than or equal to 0, and U is a rooted point. And so first set the counter to 1. U1 is a vertex that consisting of the root vertex U. The edge set is empty. The tree is U1 F1. And secondly, for I from 1 to all the way to n minus 1, do the following. Locate an edge alpha I of smallest weight such that X is in UI and Y is not in UI. Secondly, put UI plus 1 equals UI union Y. Fi plus 1 equals Fi union alpha I plus 1. And T I plus 1 equals UI plus 1, Fi plus 1. And then increase the counter I to I plus 1. And then step 3, output Tn minus 1. Here Un minus 1 is V. Okay, and then you can guess we need to prove that Prim's algorithm construct a minimal weight spanning tree. OG. And here, the spanning tree part is clear because it's a special case for the general algorithm we stated at the very beginning of last lecture. It's clear that T is a spanning tree. And denote edges of T by alpha 1, alpha 2, all the way to alpha n minus 1. And then all the minimal weight spanning trees OG, let T star, we still use the extremal method, find a certain minimal weight spanning tree with extremal properties, and then derive the contradiction. T star B1 for which the edges alpha 1, alpha k minus 1 are in T star, and k is largest. Here alpha 1, alpha 2, alpha n minus 1 is already in the order that they are put into the tree. Okay, so here also we find the minimum weight spanning tree with largest number of common edges with T. Okay, then suppose that K is different from n. If K is n, we're done. So in other words, that is T star is different from T. Then alpha K not in F star. So here alpha K joins a vertex in UK. Recall that UK is a set consisting of the vertex of alpha 1, alpha 2 to alpha K minus 1. So you have K minus 1 edges and the K vertices due to the construction. And then to a vertex in V, get rid of UK. Since T star is a spanning tree, there is an edge beta of T star joins a vertex in UK to a vertex in V, get rid of UK, such that inserting alpha K in T star and deleting beta gives a spanning tree T star star. Here I would like to draw a picture to illustrate this. So suppose this is UK, this is the UK complement, and then this is your alpha. Okay, and because it's a tree, after adding alpha, you can find a circle containing alpha. And then no matter how the circle is, it might be quite complicated, but then at least, let's use this. One edge, let's see beta, connecting, there's one edge beta connecting a vertex in UK and a vertex in UK complement. So that's how, so this is not trivial. We need to show that because from the lemma we proved in last few lectures, there's no guarantee that beta always connecting UK and UK complement. So this is a new property you need to verify. But from the picture you see, it's clear because alpha is connecting UK to UK complement. If there's no such beta, then the cycle cannot go back to UK again. Okay, then the remaining is almost the same as before. Then we have omega beta less than or equal to omega alpha k for omega t star star greater than or equal to omega t star, because t star is minimal. Omega t star star we don't know at this moment. But on the other hand, omega beta should be greater than or equal to omega alpha by the choice of alpha k. This is because, look back at the algorithm, when we determine alpha k, we seek the vertices, we seek the edges connecting UK to UK complement and with the minimum weight. So beta alpha both connect UK and UK complement. If beta has strictly smaller weight, then we should choose beta instead of alpha k. Okay, so here we must have omega beta greater than or equal to omega alpha k. Okay, and then combine these two, we know that omega beta is same as omega alpha k, and hence omega t star star is omega t star. Then we have contradiction, because omega t star star now is a minimal weight spanning tree and has strictly a larger number of edges with t than t star does. So this contradicts our assumption that t star satisfies the maximum property. It shares the largest number of edges with t among all the minimum weight spanning trees. Okay, if we look the same example for the greedy algorithm, we have the following different spanning trees. So first, the rooted vertex is A as well. Then we have AB, and we choose the smallest weight connecting to AB. Then we should have AF, AG, or BG. So let's choose AF. Then you can have FE, EG, GD, DC. Okay, you can also have some other choices. So here I just give one example of minimum spanning trees. Okay, now I'd like to make a remark for all the greedy all the algorithms generate the minimal weight spanning tree or some distance spanning trees. So here, what we do is in algorithm has the advantage that so all the data, if you look back for each step, we only care about a local minimum. We only care about one edge, which is minimum among certain properties. But finally, this is a global minimum. This is not always true. Or in other words, this is non-trivial. Because you see, I can give you an example. For example, if you have this graph of some function, this is x and y, this is fx. So each step, we just work towards, for example, this point A. Okay, A is a local minimum, there's no doubt. But then the problem is globally, B is a global minimum instead of A. Okay, so there might be some cases that the algorithm, each step in the algorithm makes your result closer and closer to A, but then the final result is in a long distance. So the global minimum is far away from it. If you study equilibrium or natural equilibrium and global equilibrium and some other theorem, this might be the case. But here, they find that even we do local minimum, finally, we still have the global minimum. So this is a pretty good case. Okay, if you have interest in this, you should study more on the global minimum, global maximum, versus the local minimum, local maximum. So all I want to say is this is a non-trivial. If you look at each step, we do something very locally and gain something globally. So from local to global is always a dream of scientists, because of the limitation of the experimental instruments or the human thoughts. We can always do local experiments. We never have a true control of the global thing. Okay, next we will generalize the above discussion to a slightly different version of network. And then next time, we will introduce some algorithm corresponding to that version and also some applications. So we generalize about discussion on networks to digraphs. So what is digraph? So digraph D equals VA has a set V of elements called vertices and a set A of ordered pairs or not necessarily distinct vertices called arcs. And so what is arc? So for example, arc alpha equals AB. So we use a picture. So this is A, this is B. And we use an arrow, means this edge is from A to B, pointed or directed from A to B. And then we call A source or initial vertex, or use the notion L alpha. And B is called the target or terminal vertex, or use the notion tau alpha. And similarly, a general digraph means multiple arcs are allowed. So multiple arcs means you have A to B several times. If you have A to B and B to A, they're not the same arc. Okay. Of course, in reality, we will not have the question like ask if this is a general digraph or not, kind of. Those concepts are constructed by human beings. The really use of the concept of digraph is in the problems, in the real problems, how we deal with more complicated situations. So if you are a little bit confused by the concept, it's okay. Just set up the one you like most. As soon as it's consistent, it's okay. As I believe different textbooks will have different version of digraphs. Okay, and here, so for example, we have ABC 3 points, and we have a lot of directed edges, arcs. So this is not a digraph, but it's a general digraph. The reason is here we have these two. They give multiplicity 2 of the arc from A to B. Okay, so similarly, we can talk about the degree, but then we have two types of degrees. So our degree of our vertex X or our general digraph is defined by the number of vertex, the number of arcs whose initial vertex is X, and then in degree of X is defined to be the number of arcs whose terminal vertex is X. A remark: for loop gamma from X to X, this contributes 1 to both in degree and out degree of the vertex X. Theorem: in general digraph, in degree x is same as out degree x, and is the same as the number of arcs, or in other words, is the cardinality of the set A. Okay, and then with general digraph, we can associate each arc with a weight as well. Obtain. Sorry. Before that, I should say each digraph can be reduced to a graph, a general graph, by forgetting some information. Obtain a general digraph. Oh, sorry. Yeah, this is the other direction. For any general graph, we can decorate it and get a general digraph. So just by giving each edge A, B, O, E an orientation, or direction, just by replacing AB with either AB or BA. And then an interesting property is the total number of orientations, OG, is 2 to the power of cardinality, OE. So in other words, for each general graph, you can associate with 2 to the power of cardinality, OE digraphs. And then conversely, given a general digraph, we can remove the direction of its arcs, then by thereby obtaining a general graph. So in other words, so if you learn a little bit fancy mathematical language, this is called a forgetful map. You forget certain actual information and derive some weak version of the object. Okay, then such graph is called the underlying general graph, OD. So the reason why we want to forget something, because the whole problem might be too complicated, and we can deal with partially, part by part. Just like for a Riemannian manifold, you have matrix on it or a sphere in R3 with radius 1. So this is a rigid object. But if you view it as a topological object, then you can squeeze in it, and so that it becomes a cucumber. Okay, the topological information is still there. So for a certain problem, you can already get some information without using its analytical part. Okay, and it's easy to see. The number of underlying general graph OD is 1. So that's a unique underlying general graph or a general digraph. And similarly, we can modify our definition of walk, paths, cycles for general digraphs. So for instance, let D equals VA be a general digraph. And then a sequence of M arcs of the form x0, x1, x1, x2, xm minus 1, xm is called a directed walk of length m from x0, the vertex x0 to the vertex xm. And then the initial vertex of the walk star is x0, and the terminal vertex is xm. And then the directed walk is called closed if x0 coincides with xm and open otherwise. We call it open otherwise. And then we denote star by x0 to x1 to x2 to all the way to xm. So here we use arrow instead of horizontal lines. Okay, and directed walk with distinct arcs is a directed trail. A directed trail with distinct vertices is a path or directed path. And a closed path is a directed cycles. Oh, here for the path, directed vertices except the initial and the terminal vertices. So in the definition, except initial and the terminal vertices. So if the initial and the terminal vertices coincide, then it's a directed cycle. And then a general digraph is connected if its underlying general graph is connected. It's strongly connected if for each pair of distinct vertices A and B, there is directed walk from A to B and directed walk from B to A. Okay, and then we also have the corresponding notion for Eulerian trail. So that means directed trail contains every arc of D. And then Hamilton path or Hamilton cycle, directed path contains every vertex of D. And I leave this to you to generalize the theorems for general graphs on Eulerian trails and Hamilton paths or cycles. To the current notion. Digraphs. Okay, now we can introduce the network for a digraph. So we still have a weight function, and in the textbook, we use a special form of the network for a diagram. That means we specify a vertex as a source and a vertex as a target. Choose as a vertex S as the source and T as the target. So in reality, you might have several sources and several targets, and then you can do the generalization of the notion here. But for our purpose, we just want to introduce you some algorithm and some general method. So we will stick to the current situation. Okay, also assume omega is non-negative. Okay, and so here is a so-called special kind of network consisting of V, A, S, T, omega. So 5 pieces of information. And then we have the notion of a flow. So a flow in N is defined to be a function f from the set of arcs to non-negative numbers, such that first f alpha is between 0 and omega alpha for all arcs. And secondly, at each vertex, the summation of the values of the flow in is a summation of the flow flows out at this vertex for each vertex. Of course, here vertex we assume is different from the source and target. As source and target, you may have net flow in and net flow out. Okay, And you might guess, what's the situation for the value at source or target? Then this can be deduced from the definition that the net flow out at the source is the same as the net flow in at the target. And I would like to make a remark that this is a discrete version of the fundamental theory of calculus, or integral by parts or whatever. So yeah, I leave it to you to digest this. Next time we will discuss several algorithms for network for diagrams and flow. Okay, I will stop here. Thank you.